Dear all, in this video we will study Otto cycle and effect of compression ratio on thermal efficiency of Otto cycle. PV and TS diagram of Otto cycle are represented over here. So in PV diagram for Otto cycle, volume at point 2 and 3 is same and at point 1 and 4 is same. That means V2 equals to V3 and V1 equals to V4. Process 1, 2 and 3, 4 are isentropic processes. Now these diagrams we have to use to find out the efficiency, thermal efficiency of Otto cycle. Basic terms used in derivation of air standard efficiency of Otto cycle. First, total cylinder volume. It is the total volume or maximum volume of the cylinder in which Otto cycle takes place. In Otto cycle, total cylinder volume is equals to V1 equals to V4 equals to Vc plus Vs. Refer PV diagram above, where Vc is clearance volume and Vs is stroke volume. Clearance volume. At the end of compression stroke, the piston approaches the top dead center position. The minimum volume of the space inside the cylinder at the end of compression stroke is called clearance volume, represented by Vc. In Otto cycle, clearance volume Vc is equals to V2. See PV diagram above. Stroke volume, that is Vs. In Otto cycle, stroke volume is the difference between total cylinder volume and clearance volume. Stroke volume, that is Vs equals to total cylinder volume minus clearance volume, equals to V1 minus V2 equals to V4 minus V3. Stroke volume is again mentioned over here. Compression ratio. Compression ratio, represented by R, is the ratio of total cylinder volume to the clearance volume. That is equals to total cylinder volume upon clearance volume. So clearance compression ratio is equals to V1 upon V2 equals to V4 upon V3. Now that we know the basic terms, let us derive expression for T2 and T3. These expressions will be useful for us to derive the expression for air standard efficiency of Otto cycle. For finding T2, we take process 1, 2, and for finding T3, we take process 3, 4. In process 1, 2, this process is an isentropic or reversible adiabatic process. For this process, the relation between temperature and volume is as follows. T2 upon T1 equals to V1 upon V2 raised to the power gamma minus 1 equals to R to the power gamma minus 1, since V1 upon V2 equals to R. So T2 equals to T1 into R to the power gamma minus 1. This is the equation number 1. For process 3 and 4, this is also an isentropic process. The relation between temperature and volume in this process is similar to the relation between temperature and volume in process 1, 2, and so T3 upon T4 is equals to V4 upon V3 to the power gamma minus 1 equals to R to the power gamma minus 1, since V4 upon V3 equals to R, that is compression ratio. So T3 equals to T4 into R to the power gamma minus 1. This is equation number 2. Now, air standard efficiency of Otto cycle. It is defined as the ratio between work done during Otto cycle to the heat supplied during Otto cycle. Air standard efficiency or thermal efficiency of Otto cycle is represented as thermal efficiency equals to work done upon heat supplied. From previous article, thermal efficiency is equals to 1 minus T4, in bracket T4 minus T1 bracket close upon T3 minus T2. After simplification of this, thermal efficiency will be obtained or after putting the values of T3 and T2 from equation number 1 and 2, we will get the equation in the form of compression ratio. This equation, after simplification, we will get as thermal efficiency equals to 1 minus in bracket T4 minus T1 bracket close upon T4 minus T1 bracket close into R to the power gamma minus 1. Again, final form of this thermal efficiency is equals to 1 minus 1 upon R to the power gamma minus 1. Now we have to understand the effect of compression ratio on the thermal efficiency, and that will be explained with the following comments. From analyzing equation of thermal efficiency, it is evident that the Otto cycle efficiency depends directly upon the compression ratio. Since the for air is 1.4 and increase in will produce an increase in efficiency. Since the gamma for air is 1.4, as increase in gamma will produce an increase in efficiency. However, the gamma for combustion product of the fuel and air mixture is often taken as approximately 1.3. The foregoing discussion implies that it is more efficient to have a high compression ratio. The standard ratio is approximately 10:1 for typical automobiles. Usually, this does not increase much because of the possibility of auto ignition or knock, which places as an upper limit on the compression ratio. During the compression process 1-2, the temperature rises. Therefore, an increase in the compression ratio causes an increase in temperature. Auto ignition occurs when the temperature of the fuel and air mixture becomes too high before it is ignited by the flame front. The compression stroke is intended to compress the product before the flame ignites the mixture. If the compression ratio is increased, the mixture may auto-ignite before the compression stroke is complete, leading to engine knocking. This can damage engine components and will decrease the brake horsepower of the engine. Thank you.